Let's start stellar black holes. We begin with stellar black holes, the most common type. They're born when truly massive stars, at least 20 times the mass of our sun, run out of fuel. The core collapses in a supernova, and if the remaining core is heavy enough, gravity wins completely, crushing matter into a black hole. Most stellar black holes weigh about 5 to 100 solar masses. Our galaxy alone may host around 100 million of them. Invisible wanderers drifting through the Milky Way. The nearest known one, Gaia BH1, is only about 1,600 light-years away, close enough to feel uncomfortably local. Intermediate mass black holes. Next are the mysterious intermediate mass black holes, ranging from 100 to 100,000 solar masses. These are the missing link. Too big to be a normal stellar remnant, too small to be a galactic monster, and still frustratingly hard to pin down. Some may form when stellar black holes merge again and again, building up mass like cosmic snowballs. Others could be ancient leftovers from the early universe, born under conditions we barely understand. Evidence is still scarce, but hints from globular clusters and dwarf galaxies suggest they might be hiding in plain sight. Supermassive black holes. At the centers of nearly every large galaxy lurks a supermassive black hole, containing millions to billions of solar masses. Our own Sagittarius A star weighs in at 4 million solar masses, while the monster in the galaxy M87 tips the scales at 6.5 billion. How did these giants form? The honest answer is we're not entirely sure. They might have started as smaller black holes that grew by swallowing gas and stars, or they could have formed directly from collapsing megaclouds of gas in the early universe. The truly weird part is timing. We've found supermassive black holes existing just a few hundred million years after the Big Bang, meaning they grew at a pace that still stretches our theories. Primordial black holes. Now we step into the theoretical. Primordial black holes could have formed in the first fraction of a second after the Big Bang, when tiny density fluctuations in the rapidly expanding universe created regions compressed enough to collapse straight into black holes. Unlike stellar black holes, primordial ones could span an absurd range, from smaller than an atom to thousands of solar masses. Some scientists even suspect they could explain dark matter, the mysterious substance making up about 85% of the universe's mass. But despite decades of searches, no definitive primordial black hole has been confirmed. Micro-black holes. Even smaller are hypothetical micro-black holes, sometimes called quantum or mini-black holes. These would be subatomic, possibly created in extreme particle collisions or existing as relics from the earliest moments of the universe. Stephen Hawking proposed that black holes this tiny would evaporate almost instantly through Hawking radiation, a quantum effect where black holes lose mass by emitting particles. The Large Hadron Collider has searched for hints of micro-black holes, but so far, nothing has shown up. Charged black holes. Most black holes we talk about are defined by just two properties, mass and spin. But theory also allows charged black holes, known as Reissner-Nordstrom black holes, which carry an electric charge. In reality, they're probably rare to non-existent, because any charge would quickly get neutralized by surrounding plasma. Still, the math is wild. 2 event horizons, strange causal structures, and physics near the center that gets very uncomfortable very fast. Rotating black holes. The most realistic and common type is the rotating black hole, or Kerr black hole. Nearly every black hole spins, because the stars and gas that formed them were already rotating. As matter collapses, angular momentum forces the spin to speed up, like a figure skater pulling in their arms. Rotation twists spacetime itself through frame dragging, creating an ergosphere, a region outside the event horizon where space is dragged along. In principle, energy could even be extracted via the Penrose process. The black hole in M87 is thought to rotate close to the maximum possible speed. Binary black holes. Black holes don't always live alone. Binary black holes are pairs orbiting each other, slowly losing energy as they emit gravitational waves, ripples in spacetime itself. Over time, the orbit tightens, the chirp rises, and then they merge into a single larger black hole. The first gravitational waves ever detected came from 2 black holes, 36 and 29 solar masses, merging 1.3 billion light-years away. For a brief instant, the collision released more power than all the stars in the observable universe combined. Rogue black holes. Now imagine a black hole with no fixed address, a dark nomad wandering through space. Rogue black holes could be supermassive ones ejected by galaxy collisions, or stellar black holes kicked by asymmetric supernova explosions. Some observations suggest there could be hundreds of wandering intermediate mass black holes roaming our galaxy. They're nearly impossible to detect unless they pass near visible stars or gas and leave a gravitational fingerprint. According to Hawking's theories, all black holes eventually evaporate through quantum effects, though this takes unimaginably long. 10 to the power of 67 years for stellar black holes, and 10 to the power of 100 years for supermassive ones. From stellar remnants to cosmic behemoths, black holes are the ultimate expression of gravity's power, laboratories for extreme physics and windows into space-time itself. And somewhere out there in the darkness, millions of them are waiting to be discovered. If you enjoyed this journey through the darkest objects in the universe, hit that like button, subscribe for more mind-bending space content, and let me know in the comments which type of black hole fascinates you the most.